Good morning, fellow mathematicians. Check out the new merch. The Infinity Grill 1 is a limited edition offer, so it's just available this month. So you better get yourself an Infinity Grill K being greater or equal to 0. Oh boy, it's so beautiful. It just fits this analytic number theory stuff so well. Infinity boy, you finally have a girlfriend. That's so Gucci. Today we are going to deal with something kind of important, something really cool in my opinion. Half integer values of the gamma function, okay? Might sound weird at first, but we can generalize this, and for this we have to take a look at three cases we will see, I will see when going through all of this, okay? At first we have to just find out one major result, and after that we can use the recursive definition to get back to this very value, and then basically we are done, okay? So it's just some handy craftsmanship right here. So we're going to take a look at gamma of 1/2. And this is, by coincidence, going to evaluate to square root of pi. Maybe you have seen this before, negative 1/2 factorial. Square root of pi. That's so surprising, Daddy! What the frick, mate? Did I just censor the word fuck? What the fuck? Okay, so how can we actually calculate this? I wanna give a little formal proof right here, okay? It's going to be a one-liner if you have a long line. And that's basically the easiest proof of the Gaussian integral, okay? There is so. We're going to take a look at Euler's reflection formula, gamma of z times gamma of 1 minus z, and that's one of the many applications of this thing right here, other than continuing the gamma function analytically to the half complex plane, yeah, to the left side of the complex plane, something like this. It's going to evaluate to pi over the sine of pi times z. We have found this out, we have proven this fact a lot of times before. Now, we want to get to gamma of 1/2, so why not bloody plug 1/2 into here. So we are going to get gamma of 1/2 times 1 minus 1/2, that's just 1/2. Ooh, what a coincidence. That's pretty groundbreaking right here. So 1/2, okay, leaving us with gamma of 1/2 squared. And this is going to evaluate to pi over sine of pi over 2. Hey, that's pretty good, it's just 1, okay? So we are going to get pi out of this. Now, in the real numbers, on the right half at least, our gamma function is defined strictly positive. It looks something like this right here, okay? That's our gamma function, meaning if we take the square root on both sides, we are going to end up with the positive branch of this thing. Exactly square root of pi. Okay, coolio. There even was a visual proof in here, that's bloody Gucci. Proving this more formally is probably not the easiest thing. Never mind. So, we got this right here, and today, like I said, we want to take a look at half integer values. Half integer values, mate. And at first we are going to take a look at when all the values in here are positive half integers. So of the form gamma of s over 2, and we want to put one little restriction on s. We want s to be odd. Otherwise this whole thing right here would make too much sense, because if you would have s being equal to 4, for example, that's going to be, well, gamma of 2, that's just 1 factorial, okay? This just spoils all the fun. Wouldn't make too much sense. So we have this right here. One case that we can consider is when s is actually equal to 1, meaning k is equal to 0. That's the first case. Leaves us with gamma of 1/2 being square root of pi. Coolio, we have done that. Now, what about other values? For example, k being equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like this, okay? We can work through this process, and it's going to make a lot of sense in a few seconds what we are going to end up with. And we are best off by putting in some little examples right here. For example, let's start off easily with gamma of 3 over 2. Remember how the gamma function works. If we have gamma of, for example, z plus 1, that's nothing but reducing this argument by 1, putting it to the front, and then we have this new argument here. Okay, that's the recursive definition of the gamma function. Gamma of z plus 1 is nothing but z times gamma of z. Meaning, if we interpret this thing right here as gamma of 1 plus 1/2, that's cool, right? Now we can use this property right here. because 3 over 2 is nothing but 1 plus 1/2. That's 2 over 2 plus 1/2. Okay, I hope you can see where this came from. We are going to get 1/2 times gamma of 1/2, leaving us with square root of pi over 2. Now, this has been free right here. What about 5, for example? Gamma of 5 over 2. This right here is nothing but gamma of, okay, 1 plus 1/2 was 3 over 2. So we are going to get 1 plus gamma of 3 over 2. It's defined recursively, okay? It's just how it works. That means we are going to get 3 over 2 times gamma of 3 over 2. But we know what this right here is. This is nothing but 3 times 1 over 2 squared. So 3 over 2 squared times the square root of pi. Let us do one more iteration and then we are going to see what we actually end up with. Gamma of 7 over 2 is nothing but, you might have guessed, it's going to give us 5 over 2 times the gamma function of 5 over 2, right? I'm terribly sorry, I was looking here and was thinking, what? Okay, we are going to get 5 times 3 over 2 to the third power square root of pi. Now we can actually generalize this, and then you can probably prove this general form by using the principle of mathematical induction, for example. I really don't care how you deal with this right here, okay? Proving this general case to be exactly right. Now, let us take a look here. We have 5 times 3 times 1 more formally, meaning we are going to multiply odd integer values together. Now, if we have gamma of s over 2, like I said, we had this being gamma of 2 times k plus 1 over 2. A nice thing is that I did right here, or a good thing, a good train of thought, is to actually take a look at the decomposition of 7 as an odd number. 7, for example, is nothing but 3 times 2 plus 1, or 2 times 3. Meaning, if this right here is exactly our s, then this thing right here is going to be our k. Just so that you see. Do we have our k somewhere? Well, we have our k down here, meaning we are going to end up with something over 2 to the kth power. This is this term right here. Also, we are going to have square root of pi right here exactly. Then we are going to have 5 times 3 times 1. I have used this trick before. Oh, okay. More formally, you would have the double factorial right here. It's a nice simplification of this whole thing, but we haven't introduced this yet, so I have to go through the whole process. If we have 5 times 3 times 1, we can actually expand this fraction right here, you could say, by all the missing parts. 2 times 4 times 2 times 4 over 2 times 4. Now, up here we are going to have 5 factorial over 2 times 4 is nothing but 2 times 1 times 2 times 2. We can factor out the 2, leaving us with 2 squared times 2 factorial, 1 times 2. So over 2 squared times 2 factorial. If you go through this process here again, on this 5 over 2, you are going to result in the same thing, just with 2 to the first power then, times 1 factorial. Meaning, what we have up here, we are going to get something over 2 to the k minus 1th power. Okay, because our k was 3 right here in this case, now we have a 2 right here. And then k minus 1 factorial. We have this exact number of 2's up here, or of k's up here, that we would have the factorial right here, k minus 1 factorial. But what do we have right here? We have to end up with 5 factorial on this occasion right here. How can we express our 5 through our k? Well, it should be 2 times k minus 1. Right here we had 5, and we would end up with 3 factorial. 5 can be decomposed into 2 times 2 plus 1. 2 times 2 is going to be 4, minus 1 is 3. So we are going to end up with 2 times k minus 1 factorial. And this should do the trick actually. Now, this looks like an absolute mess. Like I said, you can actually rewrite this as square root of pi times s double factorial. This should be the general thing that you can do. Correct me if I'm wrong right here. I haven't really digged into the double factorial stuff too much up until now. You can denote it like this. Now we can also rewrite this using our definition of s up here. Okay, s is nothing but 2 times k plus 1, because this right here is what you mostly have, for example, gamma of 7 over 2, so why not get it with respect to our s? Meaning we are going to get square root of pi over, right here we have 2 to the kth power times 2 to the k minus 1th power. Meaning in normal case this right here is going to be 2 to the 2k minus 1th power. How can we actually get to this point? So what is 2k minus 1? Well, that's nothing but s minus 2. Okay? I hope you can see this relationship. If we subtract 2 on both sides, we are going to get s minus 2 being nothing but 2k minus 1. Okay? I still have to think about everything I do right here. I'm terribly sorry. 2 to the s minus 2th power. I hope everything right here is correct. That's an ugly looking 2 that kind of triggers me and my OCD or whatever I have. So k minus 1. What is k minus 1? K minus 1 is nothing but, okay, now we can subtract this on both sides. Let us see what this actually evaluates to. I don't know right now. So if we have s being equal to 2k plus 1, we can actually get stuff to the other side. That's equivalent to saying k is nothing but s minus 1 over 2. Now we want to subtract 1 on both sides. So k minus 1 minus 1. We are actually going to get s minus 3 over 2. I hope that's correct. And also we have 2k minus 1 factorial up here. And we already had this before. Yeah, this is 2 to the 2 to the s minus 2 factorial. No, it's s minus 2 factorial. I'm terribly sorry. Yeah, this is it, right? That's a lot of number stuff right here. It is so weird writing all of this out. This right here is actually our definition for the half integer values in the right half of the real plane right here, the real nimbus. And now we are going to go through the same process, just with, for example, negative 1/2 or negative 5 over 2. Bear with me for a second. Now next up, like I said, we are going to deal with the negative half integer values. And for this we are just going to express the general form like this. Gamma of negative s over 2 in this case is going to be then gamma of negative 2k plus 1 over 2 right here. Now, this is going to cover everything that we actually need, okay? So if we want to have negative 1/2, we can actually plug k being equal to 0 into here. So we don't really have to take a look at any more k's right here if we just put it like this. The only real thing is that we now say that k is going to be strictly positive, okay? It's just element of the natural numbers with 0 intersected, okay? No, not intersected, in union with the 0, okay? The set that has 0 in it. Okay, why am I even talking like this? So never mind. Now we can go through this process, and I would like to trace all of this back to gamma of 1/2. How can we do this? Okay, so if we take a look at the recursive definition right here, we are going to get gamma of 1/2 is nothing but, okay, if we use the recursive definition, we are going to reduce this by 1. We are going to get that this is negative 1/2 times gamma of negative 1/2. I hope you agree with me that this is true. This is the first value when s is equal to 1, meaning k is equal to 0. That's nice. Now, how can we proceed from this point? Well, we are going to multiply both sides by negative 2. Gamma of negative 1/2, so the process of getting this is a bit harder than what we did before. Gamma of negative 1/2 is thus nothing but negative 2 times gamma of 1/2, meaning it's nothing but negative 2 times the square root of pi. This has been the first iteration. Now we can continue. Let us go through more examples. Gamma of gamma of negative 1/2 is nothing like, but this right here, okay? But if we want to get to negative 3 over 2, we just reduce this by 1 once again. So we are going to get negative 3 over 2 times gamma of negative 3 over 2. Now once again, going through this process, multiplying both sides by negative 2 over 3 is going to give us gamma of negative 3 over 2 is now nothing but negative 2 over 3 times gamma of negative 1/2, but we know what gamma of negative 1/2 is. It's nothing but this right here. I'm going to put it like this. I know it's positive, but it's also negative 1 squared. Keep this in mind. Negative 1 squared times, we are going to get 2 squared over 3. 1 times 3, just like before, we have to kind of use double factorials once again, times square root of pi. Let us do one more iteration and let's see if we can see a certain pattern. Gamma of negative 3 over 2. We know what this is, but once again we're going to use the recursive definition. It's nothing but negative 5 over 2 times gamma of negative 5 over 2. Now solving once again, that's equivalent to saying gamma of negative 5 over 2. I'm terribly sorry, once again I'm being pretty speech mentally disabled. Multiplying both sides by it, we are going to get, we are going to multiply the reciprocal of this thing by gamma of negative 3 over 2, leaving us with negative 1 to the third power. Then we are going to get 2 to the third power, so those powers are actually equal. That's quite nice, okay? Over 1 times 3 times 5, and then square root of pi, right? Yeah. We could go on, for example, gamma of negative 7 over 2, but at this point we probably already can see a certain pattern. Once again, I would like to start off by expressing all of this with respect to k. Gamma of negative 2k plus 1 over 2 is going to result in. Now, on 5, on 5, we actually had 5 decomposed is nothing but 2 times 2 plus 1, meaning if this right here is our s, then this right here is our k. We had a 3 up here, leaving us with negative 1 to the k plus 1 power. Okay, I hope you can see where this came from. K plus 1, that's nice. Then we have the same power up here on the 2. 2 to the k plus 1 power. Once again, square root of pi. And here comes the hardest part, you could say. We actually want to get this out of this whole ordeal. Okay, now, once again, we are just going to take a look at 1 times 3 times 5, and after that we can take the reciprocal of this thing. Then, advancing this with 2 times 4 is going to result in 5 factorial over 2 squared times 2 factorial. Okay? I hope you agree with me that this is true. Meaning, right here we actually have it pretty easy. Okay? Our 5 that we have up here in the factorial, and also we have to take the reciprocal, is actually nothing but our s that we have right here, but we know what s is. S is nothing but 2k plus 1. So we are going to get over 2k plus 1 factorial, okay? And what are we going to have up there in the numerator? We are going to have 2 to the something times this something factorial. But what is the something exactly? Well, this something is nothing but our k that we have right here. Okay? Right here we would have the same spiel, basically. We are going to get k factorial times 2 to the kth power. We can actually bring those two together, okay, to get 2 to the 2k plus 1 power. And this should actually do the trick. I don't really know right now how we can express this using double factorials. It's probably quite easy, something like s minus 1 double factorial, never mind. But now we can also write this once again with respect to our s. Okay? Now, our s is nothing but 2k plus 1, and now we can just solve for our case that we have right here. We're going to have negative 1 to the k plus 1. What was k exactly? K was nothing but s minus 1 over 2. If we add a 1 to it, that's s plus 1 over 2. And also square root of pi, we always have this. 2 to the 2k plus 1 power is nothing but 2 to the s power. K is nothing but s minus 1 over 2, and then factorial over 2k plus 1, leaving us with s factorial. And this is it. Voila. I'm terribly sorry for my speaking behavior today. I don't know why. Maybe my mouth is dry, or maybe I'm just not as smart as I think I am. No, I'm not smart. I just know how to math, at least a little bit. I think that's watching. If you did enjoy this video, please like and subscribe and recommend the channel if you like. If you want to support the channel a bit more by the features I created, don't forget, limited edition. And up until the next video, have a flammable day. I hope everything I did right here was alright. That's kind of a lot of numerical stuff. See ya.
Hat sie keine Lust gerade.